Okay, well, thank you very much. Okay, I guess my task today is trying to explain the experimental details so that the theorists in the audience can understand. Okay, so what you see here is a photograph of our magnetic trap here. It's made up of about 4,000 individual permanent magnets, and each one of them has a field strength about 1 Tesla. Okay, and then they have to be put together in the opposite orientation of magnetic magnetization. So there's a very strong repulsive force involved, and when in the process of assembling this, so this is really one of the kind of trap that we fortunately found a vendor outside Boston to put this together for us. And inside, in the middle here, is a square. It's a trap door. Okay, so we cut this into a 6 by 6 inch door so that we can lower and then let the neutrons come in and then fill this empty space above the magnets. And that's our magnet trap that we use to trap neutrons. And I'm going to tell you a little bit more detail about how we do the experiment, but the purpose is to help us trying to resolve a puzzle in a neutron lifetime measurement. But then before I get into detail, I want to start with a little bit of history. Okay, so this all started with, of course, the father of the nuclear physics, Rutherford. Okay, so in 1911, he already established the model of atomic nucleus. And in 1919, I think he measured protons. Okay, so inside the atomic nucleus, there are lots of protons, but then some people also suspect there might be something else inside the atomic nucleus. The evidence comes from, for example, helium. It has atomic number 2, but the mass number 4. So Rutherford thought that perhaps there will be additional protons there and coupled by additional electrons to balance out the charge. Okay, so that was a speculation. There was no experimental evidence at that time. So Chadwick, this is a photograph of Chadwick here, was a student in Rutherford's lab around that time. And then he graduated and then worked on something else for 10 years. But then he kept on thinking about this possibility, this hypothesis of something else actually residing inside atomic nucleus in addition to protons. So one experiment caught his eye. There was one experiment that's actually, so this is the paper published by Chadwick. So this is an experimental setup that proved the existence of a neutron. You have a polonium source here that emits some unknown radiation, okay? And that interact with beryllium, polonium emit alpha particles, interact with beryllium and emit some unknown radiation that they know is highly penetrating, is charged neutral, nobody knows what they are, and then so that's the source of this unknown radiation, and the detector here involved in a gaseous amplifier here, connected to a high voltage, and then you can measure the current created if you have ionization events, and then everything gets amplified and connect to the oscilloscope. So that's a very simple experimental setup. And he was using this experiment. So there's another picture. Oh, sorry, there's no mouse here. So this is another version of the illustration of this very same experiment. Polonium emit alpha particle bombard onto beryllium with some unknown radiation emitting. So following one French group, is actually Marie Curie's daughter, Irene Joliot Curie. She and her husband at that time was doing this experiment, and then they put in some paraffin wax there. Okay, turns out that this conversion actually converts the unknown radiation into proton, and then therefore the proton then ionize inside this ionization chamber and give you signal. So they are trying to use this reaction, trying to deduce what's this unknown radiation. So she published a paper with her husband saying that, oh, this must be high energy photons because it's charged neutral, highly penetrating, so it knocked out protons. And Chadwick at that time is thinking, something was not quite right, because the gamma ray emitted from nuclear reaction is only of a few MeV, okay? And it has zero mass, so it should not be energetic enough to unleash proton from the target here. So then he was thinking it could be this this other kind of a hydrogen electron bound state proposed by Rutherford, his mentor, 10 years ago. So he repeated the same experiment here, and then using various kind of different converter here. Then he did his kinematic calculation correctly, and then he deduced that this unknown radiation must be of similar mass as proton. And so after about 2 weeks of measurement, then he submitted a paper on the existence, on the possible existence of a neutron. Then after so here, this is the original title, the possible existence of a neutron, and then a few months later, in 1932, he submitted another more detailed paper, and then changed the title into The Existence of a Neutron. And then this paper led to the Nobel Prize that awarded to him in 1935. Okay, so that's the discovery of the neutron. Of course, nowadays we know much more about the neutrons. We know that neutrons are composite particles, okay, made of quarks and gluons, and then they are very important to initiate nuclear fission, so that has a lot of energy and weapon application. People also use those neutrons, take advantage of their wave property to study the material structure and in condensed matter, just like similar to the X-ray scattering. But however, I regret to report to you now, after more than 80 years of study, we're still not 100% sure about a lot of the fundamental property of the neutrons. So in this talk, I'm going to focus on one particular property, okay, that really get people confused in the past 10 years. That is really how long the neutron can live. So Chadwick also had a follow-up experiment that determined that the neutron mass is slightly heavier than proton. So open up the possibility that the neutron can decay, transform into proton, but of course you have to conserve charge, so then you will emit beta. That's the beta decay. Just want to show this diagram again. This is the state-of-the-art equipment in the 30s that allowed the Nobel Prize. It's not possible nowadays. So after Chadwick's discovery, then to measure the neutron lifetime with a simple polonium source is just not intense enough. So the measurement was only possible since the invention of the fission reactor here. So you have the initial measurement here using the reactor. You have plenty of neutrons coming out. You can set up an experiment to measure the neutron decay. And then a few measurements afterward, so it's all centered around above 1,000 seconds, okay, with a large error bar. And then experiment improve steadily here. So, so what's drawn here in the black curve is the particle data group average here. And then about 10 years later, then you have another improved measurement here with much smaller error bar here, but very, very different from all the previous measurement here. So it took the particle data group a few years to decide this is really the state of the art, as opposed to taking all the average. And then that actually have a sudden transition to go from 1,000 seconds down to about 950 seconds. And there are more improvement going on over the years. So there are more measurements here. And since there's one measurement here, all of a sudden you have a point here at a low lifetime, but with large error bar. That corresponds to another introduction of the new technology using ultracold neutrons. Okay, so it's a different experimental technique. The first measurement had a large error bar, but then subsequent measurement actually improved. So the later average data points here are dominated by the ultracold neutron storage type of a measurement. You see that, okay, we're pretty happy here. Everybody seems to agree. Okay, so lifetime shift, but we're okay, everybody agree here. Until about 10 years ago, okay, there was another measurement. Okay, I will zoom in a little bit more here. Oh, I guess I have to, there's one slide I forgot to explain. So this is an early beam experiment. So what the experiment in the reactor would look like. So you have cold neutron beam coming out from the reactor moderator. And then you can collimate those neutron beams passing through your detector setup. So in this setup, you will have one beta detector here. Okay, so neutron beta decay, then beta hit a detector that you can count the decay rate. If you only use one single beta detector, then you get a count rate on the order of 75,000 counts per minute. But all of them are background because it's a reactor, right? So you have a lot of things going on. You have delayed gammas, and the gamma can Compton scatter, give you electrons. So to really make sure that the electrons are really coming from neutron decay, but not from the background, so you can have a second beta detector here. Okay. So you align them so that the coincidence means you have two events triggered by the two detector. That must mean that the beta must be coming from the source that's pointed to the neutron beam. So in the coincidence rate, then you can get down to about 1,500 events per second. You say, how do I know I really cut down all the background? And then they add another detector. So you have a reflector with electrostatic potential here pointing to the graphite electrode to accelerate the protons in here. Then the proton get accelerated, then convert into secondary particles, and then you amplify those secondary particles using the electron multiplier, and then you can detect proton that way. So with triple coincidence, then you get your count rate to 1 count per minute. But still, we don't really know. We really get rid of all the background. So you can see that how challenging it is to perform measurements in a research reactor to measure a neutron lifetime. Okay, so this is the same plot here, but I only plot the data point in the past 20 years here. You have the blue data points here. Those are conducted with cold neutron beams from the nuclear reactor. You also have red data points here. Those are the data points conducted with ultracold neutrons stored in material traps. Okay, so the sudden transition happens here around 2005. I guess that's this data point here. It has the smallest error bar among all the measurements, with around 1 second uncertainty. And then they have a lifetime about 877 seconds here. Okay, and then this is many, many sigma away from the world average, which is the blue curve at that time. Okay, and then it took about 5 years for people to really convince that, okay, perhaps there's a credibility to this measurement, and then they decide to shift the world average down to closer to the short lifetime measurement. So that's a sudden change here. And then that's when the time when after I graduated from graduate school, and I think, perhaps this is a problem that I could address with the experimental techniques that we developed with the ultracold neutrons. So I just want to focus on, there are 2 data points here. The state-of-the-art bottle measurements with an average about 878.5 with uncertainty less than 1 second. Another state-of-the-art beam measurement has the world average, has the average about 887 seconds, but a larger uncertainty. But still, the deviation between these two, so each one of them is about 1 to 2 second uncertainty, but the difference is as big as 10 seconds. So it's just something that's not quite right there. So I will first talk about how the beam measurement proceeds. So you have a cold neutron beam coming through here, okay? And then the neutrons decay in flight. So you can set up a trap to trap the protons and then count the rate of the proton emerging from the neutron beam. Most of the neutrons just fly through because weak interaction has a very small rate. They just fly through, and then you have a beam monitor there to monitor the rate. And to extract the lifetime, you take the ratio of the rate of the neutron passing through your beam monitor and the rate of a proton collected by your proton counter here. It's not just that simple. You also have to know the absolute detection efficiency for each particle, for your proton counter, for your thermal neutron counter, and there are some velocity dependence here. You also have to know the fiducial volume of your trap there. So this is a measurement that's perfectly suited for NIST. It's the National Institute of Standard and Technology. All they do is calibration, okay? So they know how to do calibration very well. They figure out the way to measure the absolute neutron fluence, and then they figure out the way needed to trap neutrons. So the best measurement was at NIST. It's still ongoing. Right now they are in the second generation. So they have a quasi panning trap here to trap the protons, neutron coming in this way. And then the fluence is monitored by the neutron absorption by a thin layer of lithium-6 deposit. And it will turn the neutron into alpha particles, and you measure the alpha particle by an array of the silicon detector in the end there. It's all about metrology. So you have to know your solid angle coverage very well to know the collection efficiency, and then you also need to know your bin size very well. You have to know your deposit size very well. Okay. So in the experimental data, this is what they report. This is the proton rate as a function of the trap length. Because the panning trap has many electrodes here that you can apply different electrostatic potential. So that you can change the potential by changing, you can change the trap length by changing which electrodes you apply potential. And then in the end of the trapping, then you can lower electrode potential and then let the proton fly out to be counted by a proton detector mounted outside of the trap. So they did this measurement. The proton rate is proportional to the trap length as expected. And the inverse of the slope here tells you the neutron lifetime. But before you do such extraction, you have to know your detector efficiency, absolute efficiency. So then the measurement was done more than 10 years ago. And then they spent the rest of the 10 years trying to calibrate their various detectors. One of the first things to tackle was the neutron fluence monitoring. So the neutron fluence here, so this is their lithium-6 deposit backed by 4 alpha detector here. You put neutrons passing through here. It's a thin absorber, so most of the neutrons just pass through. They only sample some part of the neutrons that will be absorbed. And they can calculate that cross-section by knowing the thickness of the deposit. And then so they let all the neutrons passing through to calibrate such a fluence monitor. Then you need a second detector here. This out of battery here. That can totally absorb all the neutrons. So the trick is to back that neutron fluence monitor by another neutron absorber. That is the thick neutron absorber. In this case, they use boron-10. Oh, this is a different, oh, well. So in this case, that's a thick boron-10 deposit. And then the neutron interact with boron-10 will give you both alpha particle and then gamma particle. So you have an alpha detector here and a gamma detector here. And then you can measure the coincidence of these two. Okay. So I will just quickly show you the procedure they calibrate this neutron fluence monitor to kind of give you a feeling of the extent, the elaborate process it requires. So first, you will start with absolute activity of an unknown alpha source. This is a plutonium source here. Okay, it's a point source. And then you try to calibrate its activity by putting an alpha detector on the top through a collimator with a precision metrology. So you know very well the height, the opening, so you know you can calculate the solid angle very well. And then this detection of the alpha particle, because high energy alpha particle, so it's 100%. And in that sense, then you can know the activity of the plutonium source. Then after they have the plutonium source calibrated, now they mount that into their foil holder now to calibrate the acceptance of their alpha detector in the alpha gamma device here. So now, knowing the activity there, now by measuring the count rate here, now you know the efficiency of this alpha detector. Okay. Now after that, they take away the plutonium source here. Now they shine the cold neutron beam through this alpha, through this beryllium absorber, which will emit both alpha and gamma detector and the gamma. In this case, it's a thin layer so that both alpha and gamma will be collected. Alpha will not be stopped by the thickness of finite thickness of the layer. In this case, then you can transfer the detection efficiency of your alpha detector to the gamma detector. Okay, finally, they replace the thin boron foil by a thick boron foil, so you can totally absorb all the neutron flux. In this case, there's no alpha coming out. Now you just rely on the rate of measurement of the gamma detector. okay, to know the absolute measurement. Oh, thank you. So they did this. It took them about 10 years. And then they narrowed down their systematic effect by a factor of 2. Okay. And the same experiment is still ongoing. They are in the second generation. They are hoping to reduce this uncertainty by another factor of 2. And then in the meantime, they are designing a bigger trap with, to be able to accommodate larger bin waste of the cold neutrons to increase the higher statistic. They are hoping to increase the precision to on the order of 0.3 second level. So that's the bin measurement. Now, another technique to measure a lifetime is by putting neutrons in a trap. So it's the second measurement here. You pour the neutrons in the trap. Okay? If they are low energy, they will stay in the trap. You close the lid, and you wait for a certain amount of time. You open the lid, you count how many of them survive. You repeat the same measurement again with a fresh batch of neutrons. This time you wait longer, you get less neutron coming out. By repeating this, you can map out your exponential curve and then extract lifetime that way. And this is called the bottled measurement, usually involving low energy neutron. In this case, will be ultracold neutrons. Okay, so this is one example. Actually, this is the best bottle measurement. Again, that's several generations. So the first generation experiment was done in the 90s, involving in using this spherical trap here. So in this case, you have ultracold neutron coming in here, traveling down the guide into your trap. And this trap is a sphere, empty sphere, spherical shell with an opening. And then if you want to put neutrons inside the spherical volume, you rotate the opening all the way down. Okay, so that neutron will come in from the bottom. And then after some certain amount of time, you get to equilibrium density. Then you rotate this opening all the way to the top. And then those neutrons are so low energy, they cannot climb over the gravitational field by more than a meter. So they remain trapped inside the material trap. Then you wait. After a certain amount of time, then you rotate this opening down and then count how many of them survive in this way. Okay. So in this measurement here, they have several data points here. Okay, so but the problem is the neutrons, when they are inside the trap, they also interact with material surface. So they can beta decay, they can also get eaten by the surface if you have hydrogen contaminations. Okay. So to control that systematic effect, then you can measure the lifetime as a function of the neutron energy. Because the higher energy, the more likely, more collisions you are going to have with the surface. Okay. So then they drain the neutrons at a different height. Okay. So other than rotating this opening all the way down to the bottom, let all the neutrons come out at one time, they let high energy neutrons out, and then intermediate energy, and then low energy out. Okay. So then they also, again, measure different lifetime as a function of the neutron energy group, and then they have Monte Carlo to extrapolate the collision rate, and then in this case, they will extrapolate to the situation when there's zero collision rate, which is an infinite trap. And then that will be the neutron lifetime. Okay. And then you can also repeat the same measurement with a smaller size of the bottle, different material, and then see whether everybody intersect at the same point there. So this measurement was done. The first generation, so the bottle was 5 liters. 10 years later, they've done the same experiment with 7 liters of volume here. So this is a picture of the experiment. The experiment is inside this big volume here. This was done at the Institut La Langevin in southern France. They have a very powerful research reactor. And then they have a beam line here, extract ultracold neutron, a very low energy tail of the Maxwellian distribution of the thermal neutron. Come to here, have a turbine source there, redistribute the momentum so that it will let the neutron traveling down the guide, and you have a spectrometers here to allow certain energy of neutron going into your experiment here. Okay. And just recently, they have the 3rd generation of experiment, okay, much larger volume here. Okay, and now it's really grand Russian style. And this is a picture of their apparatus. So they took this very same, this set up to IL again, and then did the measurement. So in this case, it's very similar to the first generation spherical trap here. Now in this case, you have a large kind of ice cream scoop, very large. Okay. You first fill your vacuum chamber with ultracold neutrons there. And then the ice cream scoop is kind of out of the way, so the neutron can populate everywhere. So that's doing the fill. And then when you are ready to store, you first use the ice cream scoop there to scoop out some neutrons. Okay. So a lot of them, if they don't intersect, and this is the open top, so neutrons are free to come out here, but then they are trapped on the bottom here. The neutron can, if they are not in the right energy, then they will just drain out into the detector, which you can see here. And they also let some high energy neutrons leak out to shape their spectrum. After that, then you have a very well-defined energy of neutrons in your ice cream scoop, which is your storage volume, and you just let those neutrons sit for a little while. And when you're ready to detect, okay, you let the high energy neutron out, and then you detect a peak here with a detector mounted on the bottom. Now you rotate, let lower energy neutron come out, and then keep on doing this, and then you empty, and then that's the sequence. And then when there's no neutron, you measure background. And you repeat this time by holding for a longer time, and then you have a similar shape of the measurement here. Okay? So they did this measurement, and this is a photograph of what this the giant ice cream scoop looked like. It's made of copper with a very special low temperature fluorinated polymer coating to make sure that there's no hydrogen there to eat up neutrons. And then this is the researcher there trying to coat the surface with fumbling. I was told that they just use a butter knife, okay? Just scoop into your fumbling grease and just coat the surface with fumbling, and it worked. But however, even with such a deliberate control, and they even cooled down this whole giant storage volume to low temperature to make sure that the neutrons don't get upscattered and gain energy and lose the trap. Still, the best measurement, so those are the experimental data here. So the best measurement they measure is about 864 seconds there with a different trap here. But then they have to correct for their finite loss due to surface interaction to extrapolate back to about 881 seconds. Okay. So they reported a measurement with the new lifetime. It's a little bit disappointing that they didn't get to much better systematic uncertainty because they have a larger trap here. But the lesson learned from this experiment is that similar to this Russian experiment, all the previous experiments, they measure neutron lifetime much smaller than the actual beta decay lifetime because of a finite loss. And then they have to correct for this loss. Usually those extrapolation can be anywhere from a few hundred seconds to the best case is 5 seconds. Okay? So we would like to repeat this measurement and design a new measurement using new technique so that there's no need to do extrapolation. Okay, the best case is that the neutron stay inside trap. The only possibility for them to disappear is through beta decay. That will be the best measurement. So how do you do that? The trick is storage measurement, so we need to use ultracold neutrons. If I haven't told you, ultracold neutrons are very low energy neutrons. They have energy on the range of several hundred nano EV, 10 to the minus 9 EV. Because they are such a low energy, so their de Broglie wavelength of the mass is actually very large. It's several hundred angstrom. And then their equivalent velocity is only a few meters per second. So a lot of you can outrun those neutrons. Okay. How do you make them? Again, you start from what we have. You can have a nuclear reactor, fission reaction, or in our case, we use proton bombard onto heavy Z target, that the protons are fast enough to be able to penetrate through the nuclei and break them apart and evaporate lots of fast neutrons coming out this way. Once you have fast neutron, then you have to slow them down. We can use thermalization, just have them interact with bulk material to come to thermal equilibrium. So you can get down to room temperature, if you have a giant bath or swimming pool, you can get down to 30 Kelvin if you have liquid hydrogen target. But still, it's thermalization. So you only get down to like 100 micro EV. How do we get down to 100 nano EV? Okay, that involving in the trick is something we call the super thermal source. So we need a neutron to further lose energy. Okay, the trick is that so we create that lots of cold neutrons, and then we shine them through the correct material so that they will lose energy by creating the collective excitation of the condensed medium. There are several possibilities. You can use superfluid helium. You can create phonons and roton in that case. If you use solid deuterium, then you can create phonons. So the neutrons then can transfer all its momentum and energy into phonons and then becomes almost zero energy. And then once they are in that state, they just slowly diffuse out of your source and into your vacuum chamber. That's where you can mount the experiment. So this is one of the particular source that I work on at Los Alamos. We use a solid chunk of deuterium, only about 2 liters here. And the fast neutrons are produced by a spallation process of a 800 MeV proton onto tungsten target here. And you have some pre-moderation with a polyethylene slab there. And we also have some graphite and beryllium reflector to concentrate the flux of cold neutron to increase the interaction probability with the solid deuterium. So in the end, we get a cloud. So we have a pulse of proton coming in here, a pulse of fast neutron, and then that creates a burst of ultracold neutron coming out. They slowly diffuse out of this blue solid into your vacuum guide, and then they slowly diffuse upward and then travel towards your experiment. So we just had a recent breakthrough a few years ago. We get, in our measurement, we have about 200 UCM per cubic centimeter. That's actually plenty to do experiments with. And I want to show you a video of how we actually, so once we have those neutrons in our trap, how do we count them? Okay, so this is a video of my colleague, Mike Makila here. And what you see here, you see kind of in the background, the neutron guide. The neutron guide is passing through a superconducting magnet, 6 Tesla. So neutrons started from unpolarized on one end, become 100% polarized on the other end. And then those neutrons travel down the guide. In this particular demonstration, we put an end to the neutron guide here. So it's just a thin aluminum foil, just thick enough so that it can hold the 1 atmosphere pressure difference. And in this case, the neutron then will tunnel through the aluminum window into the air. And my Mark here is holding a stainless steel bottle with a similar aluminum window at the end here to try to catch those neutrons. Okay, and then some of the neutrons are captured and then get captured into this trap, and then Mark then transports this bottle of ultracold neutron physically and then dump this into a detector, which is an ionization chamber that we connect the output current amplify and into a light bulb, so you can see the counting of a neutron. Here. So the bottle is filled. Now you dump it into the detector. After a while, there's still a neutron. The efficiency is not very high, but this is what you see, yes. Yes, you just saw 5 neutrons.
So, can I ask a completely naive question? Sorry. At the end of the day, this is the gravitational trap, right? Like you have...
No, it's not. It's not our experiment. I was describing other people's experiment.
Okay, but in general, the bottles,
yes.
Various ice cream scoops, all like this.
Yep. Mm-hmm.
They're just gravitational traps, right? So even if they're ultra cold, you're relying on thousands of neutron collisions with the wall.
Exactly. Yeah, that's the beauty of this experiment. We are using all room temperature apparatus, but the neutrons, they never get heat up.
Because of those low temperature interactions.
Yeah, because it's nuclear interaction, which is very small. Okay, so if the neutrons have charge, the interaction rate will be much higher. So eventually, they will upscatter. Okay, but we're able to control. I mean, you can do a calculation. It takes them quite a long time to get upscatter. All right. So again, this is another thing. So how do those neutrons get trapped by material? So inside those material, ordinary construction material, right, carbon, aluminum, stainless steel, copper, you can calculate its nuclear potential. So in this case, I say the neutrons, ultracold neutrons, they are long wavelengths. So by the time they come to see the surface, they don't just see individual nuclei. They see a bunch of them. Okay? Each one of them has almost delta function of potential here. It's kind of just like Indian guru here, which is my ultracold neutron, sitting on top of the nail bed, relaxing. Okay? Obviously that he didn't just sink through. He gets supported. So there's an effective potential here. And then you can calculate from the material density and the nuclear coherent scattering length. And then so the trapping potential can be as high as several hundred. I think in the case of nickel isotope, it can be as high as 350 nano eV. And those are their nominal corresponding velocity. And then, of course, those materials also have finite absorption, so those are the loss that we have to combat with. So other than using nuclear force to store neutrons, gravity also plays a role because it's such a low energy. So to climb up 1 meter against the gravitational field on Earth, it would take 100 nano eV. Okay, so if I have neutrons less than 100 nano eV energy, they don't climb more than a meter. And neutrons also have spin, so then you can have magnetic interaction by passing them through a magnetic dipole. Then you can separate the spin state, or you can change this dipole into a magnetic quadrupole. Now you can store the low field seekers, one of the spin state, without using any material. And that's the technique we decided to use to construct a bottle without any material, obviously the magnetic trap. So this is another illustration here. Neutrons come to interact with the surface. Now if you add additional magnetic field here, then the neutron can be reflected without even touching the surface. So we took this concept and designed this experiment about 10 years ago. So Pete Woodstrong was instrumentation in coming out with all this magnet design. So you see that we use magnetic trapping by using highly non-uniform magnetic field we put together by a Hobart array of permanent magnets, which is the picture I showed you in the beginning of the talk. And then also to prevent those spin polarized neutrons from loss, we also have to make sure that they don't suffer spin depolarization. We have to make sure that the field everywhere is well defined. There's no field zero crossing there. So we have additional set of electromagnetic coils there to have a guiding field on top of the Hobart array holding field. And then this is kind of a cross-section of what the magnetic Hobart array look like. So it's made of several thousand individual magnets glued together. And then when you take a cross-section, you will see that this is the vectors are the magnetization direction. So you have this pointing north pole out and south pole down, but in the adjacent, and you have a magnet aligning in the parallel direction. So in this particular configuration, it enhances the magnetic field on one side and cancel out the magnetic field on the other side. And then it's this enhanced side that we use to trap neutrons. And then this is a simulation of one particular neutron trajectory inside the trap. So we put together this trap. And then this is a picture taken of my undergraduate student, Bailey. It's just before Christmas. We finished our final check, make sure that all the magnetization orientations are correct before we ship this out to Los Alamos. And then after New Year, we work day and night, okay, for about a month to put this trap into a vacuum chamber and then do precision alignment of the trap door, because you can see it's square here, right? So if there's an angular misalignment and there's a very large force involved, okay, it can possibly just destroy the trap door. And there's another video here I want to share with you. We get very excited that once we prove that we can open and close the trap door without grinding the magnets into pieces. And And then we did our first measurement with the very last week of the beam time in that beam cycle. So this is the experimental area. So the neutron source is embedded behind this concrete block showing here. The floor, experimental floor has, this has 3 experiments here. So you have the UCNA, this is the beta spectrometer used to measure the parity violation of the beta decay. And then the second experiment here is UCN tau, stand for the lifetime. This is the experiment that I'm talking about. And it has the end flange kind of open. You can kind of peek into the vacuum chamber to see the end of the Hobart array trap here. And then recently, we just mounted another EDM experiment in the second beam line. Okay. So the Hobart array now is inside the vacuum chamber. And then the trap door is in place. Okay, it's working. So we can let neutrons come in here, fill the trap, close the trap, and then measure them. Okay. So this is the first physics data. We use one week of data to collect that. Obviously, it has a large uncertainty here, but it was like within 1 sigma to the PDG value at that time. And of course, this data point convinced the funding agency saying, hey, this is really a promising technique, so give us more money to continue the experiment. So in addition to the trap and the trapdoor, we also mounted, because it's open top, okay, gravity serves as a lid. So we have a lot of space there, allow us to mount various kind of monitoring detectors. So in this case, we have a central, we call this dagger detector. It's a solid state based detector. Solid state, okay, it's not semiconductor. In our case, it's just non-gaseous. We have this scintillator coated with boron. Okay. So during the storage, this boron-coated scintillator, which is a neutron absorber, remain above the trap. When we are ready to count them, then we have a linear translational stage allow us to insert this boron absorber down. And then once neutron hit the absorber, it will scintillate. And then we have PMT, photomultiplier tubes, inside to count the event. Okay. And this is a photograph of our dagger detector here. You can see that it's boron coating with a bunch of wavelength shifting fibers here connecting to 2 PMTs, so we can do coincidence as a technique to reduce the background. Okay, those are the various details about the light yield. Okay. And also, the very same dagger detector here allows us to play the same trick to measure the neutron lifetime as a function of a neutron energy. You can let the dagger detector not going down all the way, absorb all the neutrons. Instead, you do it by steps. You first go in here, only the high energy neutrons can reach at this height, then therefore get detected. And then once you are happy enough with all the neutrons gone, and then you go to the step 2 here, you detect more neutrons at the intermediate energy range here, and then going all the way down and detect all of them here. So what's shown here is the count rate for a single detector. And then since we have 2 PMTs, we can form coincidence. And then you can see that, of course, the background is much reduced. The signal is also reduced too, but the signal to noise ratio improved quite a lot. Just count neutrons. Yes.
You mentioned this. How do you get the lifetime from that? Because this is destructive, this measurement.
That's right, that's right. So to do the neutron lifetime, you repeat this measurement again, but now this time you store neutron for a longer amount of time before you actuate the detector.
So you know exactly that whatever the process populates your it'll give you the same number each time. So presumably you do it ahead of time.
Well, ideally, it would be nice, but in reality, the beam source fluctuate. So we also need other kind of normalization technique to normalize out the beam fluctuation. So we do have those in place. Okay, so this can maybe answer the question you have. So we have filling and then doing spectral cleaning. In this particular case, we only store for about 10 seconds. We put a detector in, and then we count lots of them. We repeat the same with the same filling pattern here. You can see that we have some signal during the fill here. So that allows us to normalize these 2 measurements. This time we wait for a longer time, and we get less neutron coming out. Okay. So of course, when you do this, you also have to take into account of the beam monitor response. So in this case, by a pair of measurement of a short holding time and long holding time, taking the ratio here, just following this very simple exponential, the inverse exponential law, you can get a trap lifetime. But we know that this is a trap lifetime, okay? The trap lifetime is many, many different possibilities of the neutron loss. You can have the beta decay, which is what we're interested. You can also have neutron escaping. So neutron, no, the top is fully open. Neutron can just exit freely. You can have neutron get heated by microphonic vibration and therefore gain energy and then increase height and also leave the trap. You can also get neutron depolarized, therefore exit the trap as well. Okay, so we did a bunch of this measurement, and then we vary the different storage time here. It seems that everything, all the data point can be fit with a single exponential function. That tells us quite a lot, okay? Because if you have other kind of a loss mechanism, you will have other lifetime, okay? So then more likely you need multiple exponential to fit the data point. Okay? The fact that we can fit the data with a single exponential with a very good chi-square give us a confidence that perhaps all these other things that can plague the experiment are under control. So, and then really to understand what's really going on in the trap, because once you close the trap door, you don't really know what neutrons are doing inside. So then my student and I also did a lot of simulation. So we find out that it's quite interesting of the neutron dynamic inside a trap. So this particular neutron has high enough energy that can reach the height very close to the edge of the trap. Those neutrons are dangerous, okay? Because once they get heated, then they get lost, which is not due to beta decay. So we are very worried about those neutrons. On the other hand, lower energy neutrons, they just remain very close to the trap door here. They follow kind of a semi-periodic orbit here. And then we did some study to characterize the degree of chaos between those different trajectory, different class of trajectory. We found out that here. So we calculate the Lyapunov exponent. So you can have neutrons of some initial energy and initial angle. You can have another track with initial condition very close to them. And then just follow the evolution of these two different tracks to see how fast the position of these two neutrons diverge. And the rate of divergence is characterized by the Lyapunov exponent. So if you have a regular trajectory, the Lyapunov exponent is less than 1. If you have something larger than 1, it's mostly chaotic. Okay. So we found out that whether you have regular orbit or a chaotic orbit depend on the neutron energy. So when you have a neutron have high enough energy, say those 25 nano eV neutrons, they can reach around the middle of the trap. Then there are two branches. Some of them are periodic. Some of them start getting into chaotic region. When you get to very, very high energy, close to the trapping threshold, those are the dangerous part. And then luckily, a lot of them are chaotic. Okay. And then this helps us because we want those neutrons that close to the threshold to exit the trap very fast. So then this is a function, this is a Lyapunov exponent on the y-axis, and then this is the amount of time it takes for them to leave the trap. So we actually insert a cleaner to help us remove those high energy neutrons. We call them cleaner, it's really spectral cleaner, to swipe out all the high energy neutrons. So for the high Lyapunov exponent, it takes about 50 seconds for us to capture them and remove them from the trap. So those are the good news. They give us confidence that we can really take advantage of the theory of chaos to help us design a good experiment. So in this case, that we control the high energy neutrons by putting additional absorber here and a detector. In this case, we have the central detector can be lowered, therefore intersect with high energy neutrons and remove them from the initial population. We also have another active cleaner, again, another absorber here, but we fit it with scintillator and PMT, so we can also monitor how many neutrons are heated and can arrive at the high height of the trap. Then we have a larger cleaner here. So after instrumenting all of those changes, and then we're very confident that our neutrons remain in the trap. They don't escape, they don't get heated. The reason we know is because, so the detector signal here you see is actually two traces. One is from the short storage, and the other one is from the long storage. They get shifted in time so that they overlap. They also get shifted vertically so they overlap. But now the information you want to extract is that to see whether there's any distortion from peak to peak. If there's no distortion between these two shapes, that means the spectrum of the neutrons remain the same. So therefore, you can estimate the amount of heating that's happening when the neutrons are stored in the trap. You can also estimate the amount of insufficient cleaning that you have to correct for. And we can do this nice-step detection. We can also do a single-step detection. Just have the Decker detector go in all at once and then absorb all the neutrons. So I'm going to skip all those technical discussions, just tell you that we have lots of effects we have to worry about. Okay, you can have depolarization, you can have microphonic heating, insufficient spectral cleaning in the beginning, the detector can have dead time, pile up, and energy and phase-space evolution, and those we think that we can control to the level below 0.3 seconds. So after this, and those are our results. Our results were blinded, okay, except the first one. So the first one has a large error bar, so it's the commission data. So we published this, and it said our technique worked because we're in the same ballpark without any correction. Then the data set 2 and 3 are taken at 2 different years with 2 different blinding factors. I was in the unblinding meeting. I was actually initially in the group thinking that after unblinding, then we'll fix all the problems of the final absorption, and then that the lifetime agree with the beam lifetime, and then discrepancy resolved. Unfortunately, this is the result of the unblinding, is that we actually confirmed the previous best bottle measurement. So the conclusion after all those almost 10 years of work, the discrepancy of the neutron lifetime persists. But our contribution is that we report a measurement technique that has no extrapolation. Okay, so this is the number that we measure. Okay, and all the other systematic effect has a extrapolation size smaller than the size of our error bar. So I'm going to skip this because I'm running out of over time. But in the end, I would just to point out that the neutron lifetime is actually an important parameter for Big Bang nuclear synthesis. Okay, so the amount of the helium-3 created after Big Bang depends on the neutron lifetime. So if the neutron actually lives shorter, then you are going to have less helium-4 abundance. So then you can perhaps use astrophysics measurement here to tell us, maybe where the neutron lifetime could be. And the magenta points here is with all the input of a nuclear cross-section measurement and the neutron lifetime, you get a very precise prediction of the helium-4 abundance here. Compared to direct measurement from astrophysical observation, the astrophysical observation has a much larger error bar, but however, the centroids seem to prefer a shorter neutron lifetime. Okay. On the other hand, CMB, Planck collaboration, they are improving their technique by measuring how the photons scatter at the last instant of the scattering. They can actually extrapolate the amount of barium they have at that time, so mostly helium-4. And then they have, again, factor of 2 larger error bar, but they seem to prefer a longer neutron lifetime. So the jury is still out. We don't know what will be the final conclusion of neutron lifetime. But my summary is here that I report this new technique we developed, and then we get to uncertainty below 1 second, okay, with no extrapolation. So what reported here is what we measured. With magnetic storage, and then we keep on taking data with more statistics, improvement of the background rejection, and then we have data at hand that can get this uncertainty to about 0.25 seconds. We're analyzing this data set, hoping to publish later this year. So that's my summary. We still don't know where the PTG value should be, and then we're working hard with my collaborators. Thank you.